Hello everyone, welcome back to another video of Mario Maths. And on this video I bring to you an experiment that I want you to think about. And if you are curious about it, I'm pretty sure you're gonna go deep into it. So here I have a Galilean thermometer. This thermometer is based on the principle that the weight of water displaced is equal to the force going up on the object. So if this object over here is floating, it means, but it's partially submerged, right? It's completely submerged to a distance. By Archimedes' principle, it means that the buoyant force, which is the force that pushes it up, is equal and opposite to the gravitational force at this point. And the buoyant force is equal to the weight of the object of the water displaced, right? So that the object displaces. Which means that for varying densities of the liquid that is in where the bulbs are submerged, then the buoyant force would change, right? Because the buoyant force depends on the density of the object and the density of the fluid where it's surrounded. So if I apply a heat energy to this thermometer, clearly everything is going to start falling, because the density of the fluid is going to decrease, right? It's going to become less dense, which means some of it might evaporate. So some of it will become a gas, and it will happen very quickly. And that is why I suggest that the fluid inside is most likely a volatile organic compound. For example, ethanol could be, or hexane, or any of those organic compounds that are very volatile with very little changes in temperature. Then it will change its density very fast, and it will evaporate. Now, so here's the thing. At this very moment, we can see that the temperature tells us the temperature in the room. So how do you read it? Well, over here, the yellow temperature says 76 degrees Fahrenheit. So the metal tag says 76 degrees Fahrenheit. The blue one says 72 degrees Fahrenheit. The red one says 68 degrees Fahrenheit. And then the green one says 64. So basically 4-degree intervals, right? And so here's what we have. 4-degree intervals, each of them started with 76 degrees Fahrenheit over here. So what it means is, if one of them is on top, like in this case, and the other ones are on the bottom, then the temperature lies in the average of the temperatures in between. So the average between 76 and 72 is 74. So currently it is approximate that the room temperature right now is 74 degrees Fahrenheit. Now, right here I have a heater. So this is a heater that is supposed to have a power output of 1500 kilowatts, right? 1500 kilowatts at maximum power. There's also another setting, which I think is 500 kilowatts. Okay, so now here's the question. If I apply heat energy, to the thermometer at a particular distance, over here, of course you can change the distance, you can vary the distance, you can change the angle as well, right? Then the question is, can I prove that the heat energy coming out of this is going to be 1,500,000 joules per second? Can I prove that that's going to be the case? Only by reading the temperature change on the thermometer. So here, let's do it. If I turn it on to maximum power, let's see how fast the yellow bulb will go down. Okay, notice it's starting to fall down after about 20 or 30 seconds. At this point, I stop the heat source and no more heat energy is applied. So what happened was the change in temperature was in such a way that the buoyant force was decreasing, right? Buoyant force is directly proportional to the density of the fluid, which means the density of the fluid was decreasing proportionately as the heat was increasing. Well, the heat is always it's always the same rate, right? The rate of the heat is the same, but the total heat is increasing. So that is because the power applied is 1500 kilowatts, which is 1500 joules per second. So every second we apply 1500 joules, right? So for 10 seconds we will have 1500 times 10, right? So 150 times. So so 15,000. Now the question about the experiment is, so once this starts, well, clearly once I remove the heat source, I turn it off, you can feel the thermometer and it's a little bit warm, right? So by Newton's law of cooling, right, the rate of change of the temperature with respect to time is proportional to the difference between the temperature initially, or the room temperature, and the temperature final. So the temperature that is essentially at this very moment, the temperature is above 76 degrees Fahrenheit. So we don't really know exactly where it is. The thermometer only tells us that it's above 76, above or equal to 76 degrees Fahrenheit. So the question is, can you set up an experiment in such a way that only using this thermometer, okay, and probably a room temperature thermometer, but nothing else. And let's say, I mean, you could use a barometer, you could set up an experiment with constraints, okay? You could do anything that you think is relevant and useful to prove that only with the temperature change of the Galilean thermometer, you can see that the power output of this heater is 1500,000 kilowatts. 1,500,000 watts. So this is the heat source, right? And so, after some time, due to Newton's law of cooling, this is gonna cool down, but of course with less and less speed, right? Because it's directly proportional to the difference between the room temperature and the temperature of the object. So right now, there's not a huge difference. And that's why it's taking a while to cool off. That is why if at this very moment I were to put this on a jar full of ice, then the difference between the temperature of the object and the temperature of the surrounding is huge, which will start to have an effect almost immediately. You will start to see the balls rising quickly after you put it on a jar full of ice at 0 degrees Celsius. So that's because the difference is great, which means that because of the difference being large, then you have a greater rate of change at that particular instant in time. Now, so this is the experiment. So I recommend that you have your own constraints, right? Because if you want to solve the problem, then you might need some constraints by just looking at how fast, right, it moves. So next time I'll come up with my own solution. Hopefully, I'll be thinking about it, and then I'll bring to you what I have. So for now, thanks for watching, and make sure you try out the experiment on your own. Okay, so have a good day.